Hello everyone, in this session we will learn to model and analyze 3-span curved PSC box girder bridge constructed using incremental launching method in Midas Civil. Preferably, ILM is used when the bridge construction involves to span deep valleys, water crossing with steep slopes or environmental protected regions or any etc. conditions. So ILM can offer perfect solution to overcome these construction challenges where other construction methods fail to achieve. So ILM bridges require a high degree of technology for both design and construction and hence demand sophisticated structural analysis and design techniques when compared to other conventional bridges. So the overview of the model that we'll be generating would be 3-span 90-meter long box cutter bridge consisting of 4 precast segments having casting length of 15 meters, 30, 30 and 15 meters. So these would be match casted and would be pushed in the increments of 1 meter each. So the launching nose length I'll assume as 25 meters. So the behavior of the bridge during incremental launching and post-launching for service condition for dead load and pre-stress loads would be examined. And then we'll perform the moving load analysis as per TMH7 code. So in this tutorial you learn the following things. First, how to generate the ILM stages using ILM Wizard. As you all know, Midas Civil offers different bridge wizards which makes the modeling process real easy. Right, thereby you will be generating the whole model including the construction stages based on the information that you have provided in the wizards. So thereby making the modeling process simple, easy and error-free. Then we'll assign the static and pre-stress loads within the help of the wizard itself. Then we'll see how to define the increments of the pushing of the box structure. Then we'll perform the analysis till here and we'll interpret the results. Then after that we'll perform the moving load analysis as per TMH7 code. So the specifications of the bridge type is ILM PSC box girder curved bridge and the spans are 30 meter each, 3 span curved and 500 meters would be the radius, and the launching nose length I'll assume as 25 meters and the width of the box would be 15 meters. So I'll define the time dependent material properties as per CEB FIP 1978. Let me give a general ILM construction overview. So the incremental launching method is one of the highly mechanized erection methods used in bridge constructions nowadays. So building the superstructure in the casting yard, which would be behind one of the abutment, and each of the segments would be match casted and would be stitched to the launching nose, and the whole of the superstructure would be pushed through these pulling jacks in increments. So that's why it's called as incremental launching. So you can see the launching bearings over here. So these launching bearings would be used in the launching process and would be replaced with the permanent bearings after the launching process has been completed. So some of the key advantages of this ILM method would be maximum productivity. You could save a lot of time, and the reinforcement, assemblages and the pre-stress would be done in the casting bed, and there would be very less amount of formwork that would be involved, and you have many other advantages as well. So this would be the cross section of the box girder that I'll be using in my model. So generally the ILM bridges would be straight or will be having constant horizontal and vertical curvatures to easen up the launching process. So this would be my construction sequence that I'll assume for my model. So starting from this stage where my abutments, 2 abutments and the 2 piers would be erected, and the temporary supports, I'll take 2 supports, temporary supports in between the plant and the abutment 2, where this would be my distances. And next, the construction stage 1, I'll start my CS1, where at the end of the CS1 my structure would look like this, where in between this CS1 the process is like first the launching nose would be erected and the segment 1 would be casted in the plant and would be pre-stressed and would be attached to the launching nose. So in CS2, the bridge would be pushed for 15 meters in an increments of 1 meter. I'll assume 1 meter as my incremental push. So you can see here, like for each increments the boundary conditions would change, and hence the structural behavior changes at every push from the casting yard. So it's crucial that we need to simulate these intermediate stages as well. So Midas Civil offers a specific bridge wizard to simulate the intermediate stages between the incremental pushes to accommodate this incremental pushes of 1 meter. So in CS2, the segment 2 would be stitched to the CS1 and the whole of the bridge would be pushed for 15 meters. And in CS3, the segment 3 would be casted and would be pre-stressed, and all the reinforcement would be accommodated in the plant itself, and the segment 3 would be attached to the rest of the superstructure, and whole of the bridge would be pushed for 30 meters in 1 meter increment. And in construction stage 4, segment 4 would be casted in a similar way, and it would be attached to the CS segment 3 rear end of the superstructure, and it would be pushed for 30 meters. And if you see here carefully, so you can see here the launching nose, the distance which is 10 meters here should also be pushed out of this abutment 1. So this would be 30 meters plus the 10 meters, so it would be 40 meters in CS5. The whole bridge would be pushed for 40 meters. And next, the post construction stage, where they'll dismantle the launching nose and remove all the temporary formwork or deattach any other things, and my bridge construction process would be done. And kindly note that the segment lengths are different from the spans, where you have 3 spans here, the curved spans that I mentioned before, 30 meter each, and the segment length from starting from 1 to 4 would be 15 meters, 30, 30 and 15. So these two are different. So now let me start my model from the scratch. Let me open Midas Civil. First let me click new to generate a new file. Let me save it as, okay, I have saved the file. So let me give a quick intro of Midas Civil. So this would be the tree menu, and this would be the my model window, and these are my main tabs, and these are some of my icons. So you can see here, so you can new, open and close project, import and export options are available. So this would be my main tab starting from the view, so you can view all of the options are available. And next, the structure tab, where the wizards and the ILM bridge wizard that we'll be using is located here. And next, the node and elements, the node operations and the element operations, and to define the properties, the material properties and the section properties, all the options are available here. Boundaries, load analysis, till the tools, so you can glance through. And this would be my units, so this would be my dynamic units. I can change it whenever I want. Software automatically scales up the previously defined dimensions. So if you don't see this tree menu 2, you can right click here and select the tree menu 2. So now let me start defining the material properties first. So I'll keep the units as kilonewton meter. I'll go to properties, click on material properties, I'll click on add. Let me add 2 properties, one for the superstructure and for the launching nose. As my superstructure is concrete, I'll select this grade. See, the values have been automatically taken by the program. So you have a maximize and minimize button. So if you don't find this OK button, you can minimize it. Click OK. Click Add. Give some name. Select as 450 for my launching nose. Click OK. So these two material properties have been added. Next, I'll define the time dependent material properties. Let me change my units to Newton mm. So I'll click creep and shrinkage here. I'll click add. Let me name it as C and S. I'll select CEBFIP 1990. So all of the parameters that are required for the calculation of creep and shrinkage according to CEBFIP would be reflected here. You can change from it. So I'll give it as 50. Relative humidity I'll assume at 70. I'll take the notional size as 1000 mm. So this, don't worry about the notional size, it would be automatically calculated by the program from the specific option called change property. So I'll click show results. So this would be the graph for the parameters that I've defined. To cross check, click OK, close. Let me define the compressive strength variation of the concrete. Type in the name, select the code. So kindly note that you require mean compressive strength, not the characteristic strength. So I'll assume 8 MPa as my standard deviation. So it would be 50 plus 8. Close. So when you click the works tab, so all of the information would be automatically recorded by the program. Next, I'll define the material link. You can see here the material link. So it links the defined time dependent material properties to the general material properties, through which the change of concrete member material properties with time are automatically calculated and reflected by the software. So I'll click here. I'll select the creep and shrinkage and the compressive strength variation that I have previously defined, and I'll select my base material, by which I'll link these two time dependent material properties to my base material. Click add. So the link has been defined. Next, I'll change my units to kilonewton meter. Now I'll add the section, the box cutter section. Click on section properties, click add. So I'll go to PSC tab. I'll select PSC 1 cell, 2 cell. So as ours is 1 cell, I'll just give the name as mid section. So you can see from this figure the joints as well as the relevant dimensions you can input by looking at this figure. I'll turn on the relevant joints. To input my box cutter dimensions. So you can see from the viewer how the section is evolving as I enter the dimensions. So by seeing the viewer you can enter the values. So this is my box cutter, the mid section. I'll turn this as auto, the shear check, the Z1 and Z3 the program will calculate these distances, and similarly for the web thickness for the shear check, I'll turn them as auto, so the software will calculate automatically these distances. So you can see the calculation results. So the area, shear areas, all these parameters have been calculated by the software. Now I'll change the offset to center bottom. As the boundary conditions will be applied at the bottom, I'll take the center bottom as my reference. Click OK. Before that, let me display the offset point. So the blue is your centroid and the red is your offset. So the distance between these two would be coming to 0, and the section would be offsetted to the center bottom. So I'll click OK. So the mid section has been added to the database. Next, I'll add the section for my launching nose. I'll go to taper tab, name as nose. I'll select I section, click on user to input my values manually. I'll just take some section. So this is at the ith node, and for the jth node I'll enter some values. I'll change this y and z axis variation as cubic. As my tapering, I wanted it to take it as cubic. So y and z axis, this y and z axis tapering would be cubic. Now I'll click OK. So again, these two sections have been added. Click close. Before proceeding further, let me show a fascinating video regarding the incremental launching method construction. So you can see here the piers have been erected, and the abutment, and the temporary supports between the plant and the abutment. So my plant would be behind any one of the abutment, and I'll set up the plant. All the required formwork would be set up, and then the formwork would be erected, and the launching nose would be established on the temporary supports, and the jacks, required jacks, and the temporary formwork would be set up, and they'll place the reinforcing steel, the tendons, and then they'll pour the concrete, and then they'll pre-stress the section, the segment that has been casted here. So they'll attach to the launching nose, and the pushing starts. So with the help of this hydraulic jacks, they'll start the pushing in increments. So as the boundary conditions change with respect to each increment, the structural system changes, so it behaves differently. So we need to accommodate all these incremental push construction stages. So like that, the next segment would be casted and would be stitched to the previous segment, and the whole of the superstructure would be pushed. And these are the launching bearings, and they'll keep the sliding pads to accommodate this displacement. So like that, they'll push it. So they'll replace these plates. So this is how they cast the other segment. They'll attach it to the superstructure, and the whole superstructure would be pushed in this fashion, and the whole bridge would be completed till it reaches the other end of the abutment, and then they'll remove the formwork, everything, and then the bridge is ready. Then they'll remove all the plant and everything, and the bridge is now finally ready. Okay, let me get into the model now. So I'll go to structure tab, and these are my wizards. As you know, Midas Civil equips us with various kinds of bridge wizards, which makes the modeling of even a complex structure like ILM simple, easy and error free. So I'll click on this ILM bridge wizard. So you can see the description when you keep the arrow over there. So you have two wizards over here. One is the ILM bridge model and the other one ILM bridge stage. So ILM bridge model wizard automatically generates the analysis model of a PSC bridge by main construction stages that I have shown you before, by which it generates the model data that has the section details and the tendon placement and the tendon pre-stress details required for the construction stage analysis. And ILM bridge stage wizard defines the construction stages by automatically generating the boundary conditions for each construction stage of a bridge. So this is to reflect the changes in the structure for every incremental push. Let me first click on ILM bridge model to generate my main bridge model. So this is the dialog box, this is the wizard. By entering simple variables, you can generate the whole bridge automatically. So first you have type 1 and type 2. So and next you have the ILM model and the top bottom tendons and the web tendons. So first you can give the ILM model bridge information, bridge model, and the data regarding that, and the top and bottom tendons, those details, and the web tendon details. Let me start entering the details. First the element length. So the element length should be the multiples of one-time launching distance. I'll take 1 meter as my launching distance, and the radius of the bridge, I'll take it as 500 meters as I've mentioned before. So the convex, where the center of the circle is located below, and if it is above, then I'll choose concave. And next is the stage duration. So stage duration is nothing but specifying the number of days it took to assemble the formwork, reinforcing steel, and dismantle the formwork and the pre-stressing, everything which includes for one segment prior to the launching. So I'll just assume that stage duration as 12 days. And next the segment age. So age would be the initial maturity of the concrete segment at the start of each construction stage. So it represents from the pouring of the concrete to the prior to the launching. So I'll just take that segment age. When my segment before launching, my age of that segment is 7 days. For the launching nose, I'll take the material as steel nose section. I'll give the length as 25 meters. Next, let me enter the bridge model data. Let me select the material, C50 for my girder, and the mid section. So to define the boundary conditions to be applied in the construction stage analysis, these are the two options, the final and the temporary boundary conditions. So when you click on temporary, this would be activated, and this is the final. So before that, let me add the segments. First, the length of the segment, I'll give it as 15 meter, the first segment. And if you have the same segment to be repeated, you can change this. So I'll click on add. As you see, the boundary, the 1 meter distance from 0 to 15, the nodes would be added automatically. Now I'll add the next segment. "30 meter", 2 times. I'll click add. Next, 15 meter. Click add. So these are my 4 segments and the lengths. So my first, the final boundary condition, which represents the piers and the abutments. So the distance from the left end, so from the left end, which would be considered as the origin, 0, from there till the 15 plus 30 plus 30 plus 15, so till the 90 meter. So those would be my distances. For each 1 meter the node would be created, and this would be 1 meter length element till the 90 meters. And to choose the boundary condition at these nodes, you can select from this type. Either you want it to be support, point spring, or elastic link. You can choose from it. So as I am defining the final boundary condition, I'll click on support. First I'll select this at a distance 0. I'll click on support. Let me restrain dy, dz and rx and click define. So at 0 distance the support has been defined. So let me do it at 30 meters. Define, and at 60 meters as well. Now at 90 meters let me change the support. So I'll restrain dx as well and click define. So my final boundary conditions now have been defined. Now I'll define the temporary boundary conditions to represent the location of the temporary boundary conditions for the launching nose and the fabrication plant, which would be supported on the temporary supports. So I'll click on temporary supports. So this would be activated. So my left abutment would be considered as origin, and my right abutment is 90 meters from that origin, from that abutment 1. So abutment 2 is 90 meters. So I'll just enter the distance first, the 90 meters, and click add. So from 0 to 90 has been added. Next I'll enter 10 meters and 2 temporary supports. So these 2 distances would be added. And next 5 meters towards my plant. And my plant length is 30 meters. Take 1 meter and 30 times. I'll click add. So all these temporary distances have been created. So we can choose any of them and select the type of support to define. So I'll define all of my temporary supports as elastic link. So I'll select all this from 100 till 145. I'll click on elastic link. I'll take the elastic link length as 0.1 meter. So I can select for the link type, whether it might be general, rigid or compression. So I'll select compression and give some high stiffness to represent the temporary support and the soil. So if you want to give the beat angle, you can give as that as well. I'll click define here. So you can see the temporary supports have been defined from 100th distance till 145 till the end of the plant. I hope everything is clear in this tab. So we'll move on to next tab, that is top, bottom and tendons. So we'll define the top and bottom tendons here. Next let me select the type, whether no tendons or 1 cell or 2 cell. I'll select 1 cell. And next, to define the tendon property for the top and the bottom tendons, I'll click this 3 dot button to define the property. I'll click add. I'll give the name as top tendon TT. Select the type as internal post tension. Select the material as steel. Click this 3 dot button, select the strand diameter I'll take 12 strands, so the area would be automatically calculated. I'll give the duct diameter as 0.063, relaxation coefficient as CEBFIP 1990, and I'll take all these values as default: the ultimate strength, yield strength, and the curvature and wobble coefficient, and the anchorage slip. All these parameters would be used for the program to calculate the pre-stress losses. Select the bonnet type, click OK. Similarly, I'll define for bottom tendons. Now I'll take the strands as 9 numbers, click OK, code, and click apply. So I forgot to enter the duct diameter. I'll enter it as 0.051, click OK. For the web tendons, I'll enter the property. Give the number of strands as 30. Give the duct diameter as 0.051. And rest all I'll take the parameters as default. I'll click OK. So these are my 3 tendon properties for the top tendons, bottom tendons, and the web tendons. So for the top, I'll select TT, and for the bottom, I've defined bottom tendon property. I'll select that. So next is the tendon arrangement type. So you have 2 options here, 2 cycle and the 3 cycle. To explain this clearly, let me show you the figure. So this is my girder section, the mid girder section. So you can see the bottom flange tendons. So I'll assume these locations. I'll take 5 tendons for the bottom flange, 6 at the left top flange, and 6 at the right for the top flange, and here my web tendons would come on. So I'm just showing the bottom tendon arrangement here. So if you select 2 cycle, a group of every second tendon is stressed at a stage. That means in first group, suppose in segment 1, these are the tendons of the first group. So 50% of the tendons, like as there are 5 numbers, so these 3 tendons would be stressed in an alternating fashion. So these blue ones would be stressed first, and for the second group of the tendons, the 50% of the tendons would be stressed from first to the second segment. So these 2 segments would be stitched by these tendons, which are highlighted in yellow, and in the next stage the red ones would be stitched from the segment 2 to segment 3 in alternating fashion, and till the segment 4 where all of these green as well as the black tendons which are highlighted would be stressed. So this is what 2 cycle mean. So I'll go back to the model. So if you select 3 cycle, so that means in a group every third tendon would be stressed at a stage. So that means in the first group 1/3 of the total tendons would be stressed in the first segment, and in the second group 1/3 of the total tendons is stressed of the first and the second segment, and in the third group 1/3 of the total remaining tendons would be stressed over the first, second, and the third segment, and it goes on for the subsequent stages till the last 2 segments, which would be reverse of the first 2 stages. So this would be very clear when I show you in the model. So let me proceed by selecting 2 cycle here. Next is the tendon A jacking order. So you can see from the figure the A, so you wanted it to be stressed at first, so I'll select first, and tendon B as well for the bottom tendons. I'll select first. And for the jacking stress, so for the top tendons, so SUY is your ultimate tensile strength of the tendons, SY is the yield strength. So I'll take this as ultimate and this one as well as ultimate. And next, the grouting. So these options are used to tell the software for the timing of the grouting. So if you wanted the grouting to be done at the pre-stressing, means at the time of tensioning, you can select this, or at every one stage. So that means if you pre-stress the tendons in CS1, so if you give this as 1, then the grouting would be done in the next stage. So this means the increment. So I'll keep this as 1. Next, I'll take some values. So you can see this B1, B2 and all these values from this figure. So these are all self-explanatory. So I'll enter the values. Take B3 as 0, H1 as 0.165, so ST is your spacing of the top tendons and the bottom tendons as B. So I'll take number of tendons as 3 here for N1, N2 3 and 3 as well. So when you select type 2 over here, so that the user can manually define the tendon layout. So from here you can define the position and the locations of the tendon. So you can give the baseline distance. From there, this distances towards the tendons. So you can manually give the tendon locations from these parameters. So let me choose type 1. So now my top and bottom tendon locations I have defined. I'll go to web tendon tab to define my web tendons. So you can select the type for the web tendons. If you don't have any web tendons, you can select none, or the type 1 or the type 2. So when you click on type 1, so if you have the continuous tendons which are shown in this figure, so you can select the type 1. So if you have type 2 where you have the anchorages and the blisters, so you can go for type 2. So I'll go with type 2, and for the first tendon, for second and the third, that means for the all of the tendons, I'll select web tendon property that I've defined previously, and the jacking stress I'll take 0.7 SU, and all these parameters which are given in this figure, the details and the lengths respectively. So you can see the figure and enter the parameters accordingly. So I'll assume some dimensions, I'll enter them. So H is this distance to the reference, and from that the G1, I'll take G1 as 0.24, G2 as 0.15, .2, S1 I'll take it as 0.38, this is 0.2, so A and B would be my straight anchorage lengths, A and B. I'll take that as 4 meters. So to define the position of the web tendons, you can enter these details by seeing this figure. EY would be the distance till this point, and this red line represents the center line for the web tendons. So I'll give this distance as 2.503 and take the angle as 16.39 degrees. Next, we can specify the timing of the grouting so that the program will take the transformed sections for the calculations. So I'll take this as one stage, and if you click on type 2 here, so all the parameters are there for you to edit by seeing this figure. So you can define your own tendon, the web tendon, manually. So you can see the distances and the details. So all these things you can edit and form the tendon locations that you required. So I'll go ahead with type 1. So before clicking OK button, let me save as the wizard. So you can directly save the wizard data into .wzd format. Let me give some name. So you have the open option, so you can recall the wizard even after closing the program. So all the data would be updated. So this is an interesting feature, so that you can use this as a template and you can use for sharing. So I'll click OK here. So you can see here the model has been generated. Starting from the structures, the node and elements according to the dimensions and the data that we have fed into the wizard, and the material properties, the time dependent material properties, the sections, and the tapered group for the nose. Automatically the software has taken that, and the supports, the boundary conditions. You can click display. So these are my final boundary conditions and the temporary boundary conditions, and the elastic links for the soil that we have defined in the wizard. As my bridge is curved, so my support axis would be rotated with the node local axis feature. So in plan, if I show you, so you can zoom in. So the axis has been rotated. So my supports would be correctly defined. Next, the static load cases, self weight and the pre-stress loads, and the profile have been automatically defined according to the dimensions that we have specified in the wizard. So you can see the web tendons, the bottom and the top flange tendons, the tendon properties, tendon profiles. So we have defined 51 profiles, and the construction stages, and the groups which would be used in the construction stages. So the structure groups, the boundary groups, and the load groups that the software has automatically defined. So let me undisplay them. Go to front view. Next, allow me to explain the construction stages that the program has created after we ran through the ILM bridge model wizard. So this is my base condition, and these are the construction stages. So you can see from here, from the tree menu, all the information would be recorded. So here the CS1 to CS4, the stage duration is 12 days, and CS5 and CS6 0 days. So we'll later on change the CS5 and CS6 duration to account for the time dependent effects. So let me switch to the construction stages to show you graphically. Before that, let me click on this display options and turn on all the loads, apply, and even the boundary conditions. So all the loads and the boundary conditions would be shown simultaneously. So I'll switch to CS1. So in CS1, the launching nose and the segment A would be there, and the alternating tendons would be stressed, as you can see from here. And there are no boundary conditions that are applied in this stage. So we'll be using the next wizard, which is the ILM bridge stage wizard, to define these boundary conditions as required and to account for the incremental push. So I'll switch to CS2 now. So my segment 2 would be stitched to the segment A and the rest of the superstructure, and the alternate tendons would be stressed from segment A to segment B. So from the top view it would be clear. So I'll switch to CS3. So my alternate tendons would be stressed from segment B to segment C, and CS4 segment D would be stitched to the rest of the superstructure, and all of the tendons would be stressed, and there are no boundary conditions, kindly note that. And CS5, the web tendons would be stressed, and in CS6, so we'll account for the time dependent effects in CS6, so we'll later on change the duration. So let me get into the base. So you have to go to the base to edit any of the parameters. So I'll click this button, define construction stage. So I wanted to see the construction stage definitions in CS1. So you can see in the element boundary and load groups, the element groups. So the nose and segment 1 for the maturity was taken as 7 days in CS2, and these are the elements, so you can switch between them and see. So in CS4, segment 4 would be stitched to the rest of the superstructure, and there are no boundary conditions in between CS1, CS2 and CS4. And the load CS1, sulfide would be activated at the first stage, that is CS1, and next the pre-stress group 1, in CS2 second pre-stress group till the 4, and CS5 the web pre-stress has been activated, and CS6 we'll later on change this. So I'll click cancel, I'll just close it. So next let me undisplay all these loads and boundaries. I'll click reset all, click OK. So next I'll move on to my second bridge wizard, the ILM bridge stage wizard. So this is used to define the construction stages by automatically generating the boundary conditions for each construction stage of the bridge. So this is to reflect the changes in the structure for every incremental push. So this is my wizard. So here we have two boundary groups which we have defined. If I go to groups, so you can see here, so these two groups were created from ILM bridge model wizard that we used previously to define our model and the main construction stages. Now we'll define the sub construction stages through this wizard. So first the boundaries of the final system, so I'll select the final boundary group. Next the generation tolerance, so this is to specify a tolerance value within which an eccentricity between the location of an element node and a boundary location can be ignored during the launching. So I'll take this default 9.14 mm, and let me change my units to meters, kilonewton. So next is the launching direction. So next is the reference node. We need to specify the reference node to determine the direction of the launching. So I'll give this as the front end of my launching nose. I'll give this as 1, which would be this node. You can select directly as well. So next is the start node. So assign the node location for which the reference node will start. So the position we need to assign, so I'll just give the node number as 116. So you can see where the 116 is, so you can type in over here. So this is my 116 is the start node, and I'll give the end node to determine the direction of the launching. So I'll give this node which is adjacent to the start node, which is 115, and I'll give the radius of my bridge, which is 500 meters. So counterclockwise or clockwise, I'll select clockwise. So next is the launching information. So these are all the main stages that have been previously defined by the bridge model wizard, starting from CS1 to CS6 as I shown you before. So the duration, which was taken as 12 days till the CS4. So next let me define the launching information for the each construction stages. So I'll select CS1 first, click on define. So first we need to specify the distance. So the distance would be the length of the segment. So my first segment is 15 meters, and I assume that the launching increment would be 1 meter. So the steps for the launching would be 15 steps, and let me save the construction stage results and the sub stage results, which are step results. Select this. So next you can activate and deactivate the temporary support. So I'll select this temporary boundary group and click activate here. So the software automatically takes care about the change in this boundary conditions with every step forward. So I'll click OK here. So you can see in CS1 the stage steps results have been defined. Next, in similar fashion, I'll define CS2 steps. So the distance would be 30 meters for my segment B. So I'll click save this results. I don't need to activate again the temporary supports, because once they have activated at that stage, till the deactivation the boundary group would be activated. So I'll click OK here. Similarly for CS3 I'll define. Save the results, click OK. For CS4 my distance would be 40 meters, so that my launching nose will be coming out of the abutment, so as I shown you before. So I'll give the steps as 40. Save the stage step results, I'll click OK. So now in CS5 there's no launching of any segments now, so I'll just deactivate the temporary supports. I'll click add here, I'll click OK. And CS6, as this is used for the time dependent effects, so I'll just give the launching as 0 0 and just save them. I'll click OK. So before clicking OK to run the wizard, let me save the wizard. I'll just give some name. Okay, so later on you can open the wizard as well, so you can recall the wizard. So I'll click OK here. Okay, so the wizard has been ran. So I'll go to front view. So as per the information that we have given in the bridge stage wizard, the software has thereby created all these boundary groups. So I can click here to list out the construction stages. So I can see here the main construction stages have been subdivided as specified in the bridge stage wizard. So according to them, till CS6. So let me switch to the graphical mode, where I'll display all these boundary and the load simultaneously, and I'll switch between the construction stages to see my boundary change and as well as the load change with respect to the construction sequence. So I'll go to CS1 first. So the information regarding the CS1 would be listed in the works menu. So I can see the supports and the elastic links that are applied in this CS1. So I'll zoom in here to show you the temporary supports. So you can see this supports, so which are the top of the elastic link. Okay, so these are restrained with respect to the Y translation and rotation about the X. So we are resisting the torsion and the Y translation, but not the Z translation. So in Z direction they are free. So while the pre-stress, there can be an uplift of the girder or the hogging of the girder, so that we will be allowing. So this is my CS1 and this support would be hinged. So this is my abutment 2, where the launching nose, the tip of the launching nose would be resting in the CS1. Then my pushing starts from here. So CS1 I'll which is a substage, I'll go here. The 1 meter pushing would be done. So my support conditions change, and this would be the cantilever part of the nose. So all the segment A would move along with the launching nose forward in the 1 meter direction. So I'll go to CS2. So this would be again 1 meter push. So like this, there would be an incremental push of 1 meter for each construction stage. So I'll go to CS1 15 and then CS2, where my segment B would be stitched to the rest of the superstructure. So this segment B, which is of 30 meters, is supported on the soil in the plant. So that is reflected over here in CS2. All the boundary conditions would be here. So you can anytime later on change any of the parameters like the boundary conditions or any loads which are coming onto CS2. You can apply them after running the wizard. So I'll go to CS21. So this, from there the incremental pushing would start. So the pushing would be done till the 30 meters. And then CS3, where my segment C would be stitched to the rest of the superstructure, and the pre-stressing would be done, the alternating pre-stressing, and then the pushing would start from CS31. So here till CS330, so 30 meters incremental pushing would be done. From here CS4, where my segment D would be stitched to the rest of the part and the pre-stressing would be done in this stage itself, and then the pushing starts from CS411. So this would be pushed till the 30 meters. So you can go to front view. So you can see here this distance should also be pushed. That's what I was mentioning, like the 30 meters push has been done till here, and then this distance is 10 meters. So that would be 30 plus 10. So this launching nose should come out of this abutment so that we can dismantle this launching nose, and the superstructure would be ready on the actual final boundary conditions. So till 30 plus 10, so this would be pushed like this, the launching nose out of this abutment. So CS 440. So my bridge is ready now. So in CS5 I need to dismantle this launching nose, so I have to remove this. And CS6 I'll define the time dependent effects. So I will be capturing the time dependent effects in this CS6. So I'll go back to the base model to edit the parameters. Now I'll undisplay them. Click OK. So let me modify my CS5 and CS6. I'll go to load, construction stage, define construction stage, or you can click this shortcut icon. So I'll go to CS5 and click on modify. So now I'll select this nose element group and then click on add in the deactivation tab. So then click apply. Now I'll switch to CS6. I'll go to CS6. I'll give the duration as 10,000 days to simulate my time dependent effects. Then I'll click apply. Now I'll go back. So these are all my construction stages. CS5 indicates the removal of the launching nose, and CS6 for the time dependent effects. So now I presume now I'll see the construction stages. They seem to be fine. Now I'm ready to perform my analysis. So if you have any other loads which are coming on to the structure, like the temperature loads which are coming on the construction stages, you can define them, group them, and then use it in the construction stage definitions. So you can define in the base stage itself, you can go to the loads, different type of loads. You can apply the dynamic loads, you can perform the response spectrum, you can analyze with the moving load and the heat of hydration and the temperature loads if you have any. So these are all the loads which would be coming after the construction, that is the post CS. So you can simulate that as well. So let me click on perform analysis here. Okay, so the analysis has been completed. You can see here it just took 265 seconds, even for a structure like this where you have a lot of boundary conditions and the different type of construction stages. So you can appreciate the solver performance of Midas Civil. So let me get into the post construction stage. So you can see here there are two additional stages that have been created by the program after the analysis. So it's min max indicates this stage where the maximum and the minimum results would be obtained in this stage of all the construction stages summation, and this would be my post construction stage where all my post construction stage results would be available for you to view. So now we are into the post processing mode. You can see this lock option, so you can't edit the model now. So for that you have to go to the pre-processing. So I'm in the post processing. Let me show you the results. I'll go to results tab. First let me click on this load combination. So from here you can create your own load combination. You can name it. Let me give some name. So these are the results of the construction stage. At the end of this construction stage, so CS indicates the construction stage, the dead load. I'll just make a combination of creep secondary and the shrinkage secondary. You can give the factors as well. Okay, so this is my combination. So unlike other programs, you can change this load combination anytime you want and you don't need to run the analysis again. So that's the advantage. You can auto generate the load combinations. So all these options are available. Click close. So next, first let me go to the reactions. So I'll switch to the construction stages, suppose CS6. Go to works tab. I'll go to display options. Let me display my boundaries. So these are my boundaries. So the two abutments and the two piers. So let us see the reactions. I'll click on summation. Summation is the addition of the dead load, tendon primary, secondary, creeps secondary and shrinkage secondary till here. So all this summation. So FZ vertical component. I'll turn on the legend. So these are my reactions. 7301 kilonewton is the maximum reaction at the support 2. So you can switch between the different construction stages to see the reactions in between. So next I'll go to the deformations. I'll select the stage as CS6. At the end of this CS6, I'll select the last step, that means the end of CS6. So I'll click apply. So this would be my deformation. So this is highly exaggerated one. So if you wanted to see the real displacement, you can turn on the real displacement. So this is how in reality the structure would look like. So my deformation is almost like 0.03 meters. I'll change it to mm. So in X direction it's 26 mm and in Z direction it's 4 mm only. Now let me go to the forces beam diagrams to see my bending moment diagrams for different construction stages. So I'll click on post construction stage, go to front view. I'll turn off this deform, select MY as my component. I'll click apply. So this would be my bending moment diagram. So you can see the values. I'll just turn to kilonewton meter. So you can see the bending moment diagram variation. So you can locate the maximum bending moment from this variation. So this is the load case that I've chosen for the combination. Similarly, I can switch between the construction stages to see the bending moment variation. So for the dead load, this would be my bending moment diagram, and for tendon primary, so this would be the bending moment diagram. Similarly for the summation, so I'll go to CS5, click apply. So from CS5 to CS6, which indicates the time dependent effects which are considered in CS6. At the end of CS6 you can see the increase in the bending moment diagrams. Now I'll go to some other construction stage like CS4. So you can see the bending moment variation to CS4. So you can see the hogging movements and the sagging movements at the location based on the launching positions. Now let me get into the stresses. I'll click on stresses, beam stresses diagram. So this would be the maximum. So these are the points 1, 2, 3, 4. I'll select summation. and I'm in CS3. I'll click apply. So this is my stress diagram. So these are my stress results. I can change it to Newton mm. So you can appreciate the results part of the software, which is very intuitive for the user to locate his critical sections for the design. You can switch between different construction stages to see the stress variations. Go to post construction stage. So this is my stress variation after the construction, which is post CS stage. So if you wanted to see all the results in the tables, so automatically the software will tabulate all the results. So you can go here, select the load combination. I'll turn off at the part J. I'll click OK. So neatly the program has listed out the results. So you can, this is like Excel friendly. You can directly copy and export to Excel. So these are the beam stresses for all the elements that are listed out. So I'll go back to my model. Okay, so next let me show an interesting feature called as bridge girder diagram. Click on it. So you can switch to some construction stage, suppose CS6. So I'll select the last step and the load case as the summation, and you need to select the element group for the bridge girder, as we already have this bridge girder element group. So I'll select that, which includes my superstructure. So I'll select combined and I'll click on this draw allowable stress line. I'll check on that. I'll give my allowable compression as 8 MPa and this 3, and the current stage results. I'll click apply. So a stress diagram would be generated for the entire girder, the superstructure. With respect to the distance, you can see the stresses, like negative is the compression, MPa. So you can see these guidelines which will guide you through locate the elements which have crossed this stress limit. So you can zoom in the portions and then zoom out. So for the entire bridge girder, you can check the stress variation simultaneously from this graph, and you can see the max and min values. So in similar way, I'll show you how we can see the bending moments. I'll click apply. So you can see this would be the bending moment variation throughout my bridge length. So you can see the maximum and minimum. So this is at this distance, so you can locate the maximum and the minimum. Similarly, you can see for the other components, for the shears, this would be the shear force diagram. You can directly save this image. Okay, so I'll go to Midas, click close. Next, I'll show you how we can extract the moment history graph for all the construction stages of a particular element. For that, you can click this option, stage step history graph. So here I'll select beam forces and click on add function. I will turn off this option. I'll select this element. So I'll give some name, first span midsection. So I'll select the component as M by and ith node. I'll click OK. So this function has been added to the list. I'll select it, and for the multifunction last step and the stage step result, I'll select, and I'll select the summation component, the load case, and click on graph to generate the moment history graph of this element for all the construction stages. So you can see from here. So on the x-axis you can see the different construction stages starting from CS1 till the last. So for that element, how the moment diagram is varying, what's the moment, you can check from here. You can zoom in and zoom out, and you can save it as text so that you can see the values. Okay, so like that you can check the nose tip deflection as well. So I'll go to CS1, I'll select displacement, click on add new function, I'll write the name as nose tip deflection. I'll select the node number as this one, which is my nose tip. I'll select vertical, click OK. So this has been added. I'll select it, select the summation load case, click on, give the nose tip summation. I'll click on graph to generate my graph for the displacement history of the nose tip. So this is the nose tip deflection. So you can see here from the CS1 till the end of the construction how the nose tip is deflecting. So you can look at from here. So in ILM construction sequence, the nose tip deflection is very important, as we need to monitor the nose tip deflection to reach the correct boundary conditions. So you can check from here. So you can save it as a text to see the values of this graph. So now I'll go to Midas. Now I'll go to post CS and click on the results table, go to tendon, click on tendon loss. So you can select the tendon group from here and the construction stage where you wanted to see the tendon pre-stress, click apply. So stress after immediate losses, elastic deformation loss, the stress loss, the creep shrinkage, relaxation loss, all this would be tabulated. You can cross check, and the final stress ratio, which is 0.84%, is remaining after CS6 in this tendon at this location, at this element location at the ith. So this is the stress percentage. So like that you can switch between different tendon groups and you can see the losses. In similar fashion you can go to tendon. If you want to see the tendon elongation, you can click here so that you can see the tendon elongation for different tendons, as well as the element elongation and the summation. So all the things are neatly tabled out. So these are all Excel friendly. You can copy them to the and export to the Excel and later on check the values if you wanted. So now let's perform the moving load analysis. For that I'll click on this unlock button to get into the pre-processing mode. I'll be in the base stage. I'll go to load, click on moving load and select the moving load code as South Africa. I'll click yes here. So this is with respect to TMH7 code, which is 1981. So first you need to define the traffic line lanes if you are using the line element model. So if you have any plate element model, then you can go for traffic surface lanes where the loads would be applied as the pressure loads. So moving load is a three-step process. First you need to define the lanes which would be on the bridge, and then the vehicles that would be coming onto the lanes, and then the moving load combination of those vehicles on the bridge. So first let's define the traffic line lanes. I'll click on here. So here I'll click add to add the lane 1. So I'll type in the name as lane 1. I'll change the units to meter, kilonewton. I'll take the lane width as 3 meters and this is the eccentricity. So you can see from this figure, from the reference axis to the center line of the lane would be the eccentricity. So you can see from here, so I'll consider these lanes. I'll take my carriageway width as 12 meters. So I'll assume 3 meters lanes of 4 numbers, and from the center line, which is my element line, from there the center line of the lane 1 would be 4.5 meters. So this would be my eccentricity for lane 1. Similarly for lane 2 it would be 1.5 meters and this would be symmetric. And regarding this traffic lane optimization, if you see in this figure, if your lane width is more than the width of the vehicle, then the program will switch this vehicle in 3 positions to check the maximum effects, right? In the center and the left side and the right side. So let's define this lane 1. I'll take the eccentricity as minus 4.5 as shown in the previous figure. I'll turn on the traffic lane optimization, select the lane element for the vehicle load distribution, and we need to select the reference axis by 2 points, but as our bridge is curved we can't select by 2 points, so we can go for picking or the number option. So I'll take this element number as 26 to 116. If you want to see 26 to 116 elements, so this would be my superstructure. So now I'll click add here. So you can see here, so the eccentricity is based on the elements. Now if I click OK here, so you can see the lane would also be curved. So you can appreciate the feature of the software that if the elements are curved, then your lane gets automatically curved. Now let's define lane 2. Similarly, I'll give the name as lane 2 and give the eccentricity as minus 1.5. Now I'll click add. Click apply here. Now I'll change this name to lane 3. Now I'll give my 1.5. I'll delete this existing table. Click add here. Click apply. Again I'll delete this table. I'll change this to lane 4. Give the eccentricity as 4.5 plus this time. Click add. Click OK. So these are my 4 lanes. Click close here. Right click and display on the traffic line lanes to display all the lanes simultaneously. So you can see here this would be my lane 1, lane 2 and lane 3 and lane 4. So this is my reference axis. We have given the eccentricities from this reference axis to the center line of the lane. Now let's define the vehicles. So I'll click on this vehicles. I'll click add standard. So here it's TMH7 standard load. Here you have 3 type of vehicles like which are available in the code NA, NB and NC. So if I click NA, you can see this figure. And the unit length for the loaded length increment, by default it would be 1 meter. I'll click apply. So this gets added. Now I'll choose NB as well. So you can select the number of units. I'll take 36. Click apply. Now I'll choose NC. So you can see all these distances which are there in the code are available here. I'll click OK. Click close here. So now we have defined the lanes as well as the vehicles. Let's define the combinations of the vehicle that would be coming onto these lanes. For that, I'll click on define moving load cases. Click add here. So here I'll give the load case name as LCNA for my vehicle NA. So I'll select the load model as NA type, select the vehicle as NA. As the code provision goes, you can select all these lanes for NA. So the whole bridge would be loaded by NA loading. I'll click apply. Now I'll change this to NB. So according to the code of TMH7, for NB type you need to select only 1 lane onto the bridge. So let me select lane 2. For simplicity, I'll click apply, and then now I'll change this to NC. So this is my NC vehicle. Similarly, I'll select the lane 2 for NC, as only 1 NC load would be there on the bridge. I'll click OK. I'll click close. So now you can see we have defined the lanes, vehicles and the load cases where all the combinations of the vehicle coming onto the lanes would be are defined. So One more thing, we can define the concurrent reaction group so that the software will provide you with the concurrent reactions for the design of the substructures if you want. So for that concurrent reactions, you need to have the concurrent node group, which is your supports. So we'll define that. So I'll right click here, click new to add the name, give some name. So let me undisplay the lanes. So I'll go to display option, go to boundary, turn on the supports. So in CS6, this would be my superstructure. So we need to pick this nodes. So this node numbers would be 26, space 56, 86 and 116. So you can check that. Okay. So now as I've selected, I can drag and drop this group. So for that you need to be in the base stage, drag and first into 26, 56, 86 and 116, drag and drop. So this gets selected. If you double click, you can see those node numbers have been grouped under this reaction group. Right, now we'll click on this concurrent reaction group. Now we'll select this, so this program will automatically check the concurrent reactions at these node levels. Click OK. Now we are ready to perform the analysis. I'll click on this perform analysis. Okay, so to save time, let me open a model where the analysis has been already performed. Okay, so the analysis has been performed. We can go to results to check the results. Before that, we can make the load combinations here. So this was my previous combination which I have made. Now I'll give MVL some name. Now we can see the load cases that we have defined would be available. So the results of this load cases are available so that you can make the load combinations out of it. So I'll select this load cases and I can directly make an envelope. So max and min effects would be captured by this envelope. Now I'll give some name like ULS. Now I can pull these two load combinations which are already defined. Like I'll select this and I'll select the envelope. So now I've taken the maximum effects into this ULS. I'll click close here. So here first let's see the deformations. So I'll select this load case, click apply. So this is a highly exaggerated one, so you can change this to related, and this is my deformation. So you can turn on the legend. So you can see the deformations are almost negligible, means it's very less. You can change this to mm. It's almost like 0.81 mm. So like that you can check even for envelope. So 6 mm. Similarly, I can go check the bending moment diagrams for the ULS. So this is my bending moment diagram for the envelope. Similarly for the max and min. So you can turn on the values and check. Similarly the stresses, beam stresses diagram for even for the moving load, like for the moving load envelope, you can check the bottom stresses. So I'll change this to Newton mm. So these are my stress profile along the bridge girder. So now let me show the interesting feature called moving load tracer. So by which you can actually trace the position of the vehicle for the maximum effects. Suppose I have taken the beam diagrams and I have selected ULS, or I'll select NA max. I'll click apply. So this is the element where my max bending moment is coming, 39 element. Now I'll go to moving load tracer, click on beam forces. So these are all the reaction, displacement, thrust, force, beam forces. So for maximum and minimum effects, you can trace the position of the vehicle. So I'll select the key element as 39, where my maximum bending moment is coming. Now I wanted to know the position of the vehicles which is causing that maximum bending moment. So I'll click apply. So this is the position of the NA loading for that element the maximum effect is coming. So you can see there is a incremental decrease after this 36 meters length, the NA loading, which is according to the clause, according to the code. Similarly, you can see for the NB. So you can see we have selected the lane 2 in which the NB vehicle is running. You can see the wheel load. Now I'll select NC load. So you can see the NC load for which the maximum bending moment is occurring at that 39th element. So you can even write this to a file, and you can actually change this to a static load. So I'll write this to a file, this load position, and then you can copy and then paste directly in the MCT command shell and hit run, so that a static load of this vehicle position and the load would be created. So right now I'm not doing so, thereby the analysis results would be deleted. So that's why I want to show you the concurrent reactions. So you can actually get the concurrent reactions. You can go to results, click on results table, click on concurrent max min reactions, and click apply. So these are my concurrent reactions. So for FZ, what would be my other reactions and other effects for this maximum, right? This is regarding the concurrent reactions. Okay, so we'll end the webinar here. So if you have any questions, you can write to us at techsupport@midasit.com. So thank you all for attending. Thank you.